There are a lot of different units for solution concentrations. And there's also qualitative terms. Dilute and concentrated. Dilute has less solute per given amount of solvent, and a concentrated has more. And those are relative terms, just like rich and poor are relative. It's like, well, what are you comparing it to? You might be poor compared to Steve Jobs or somebody, but you might be very wealthy, very rich compared to someone in a third world country, right? So it's a relative term. So these are some of the concentration terms available to use for solutions. And we're going to look at each of them. We've already learned about molarity. Molarity, again, is moles per liter. There's also molality, mole fraction, mole percent, parts by mass. We've looked at percent. We can also have parts by volume. So this table is a nice reference as you do some homework and do some studying. So molarity, we looked at this back in section 4.4, but it's probably the chemist's favorite unit, so it's very important to understand. Molarity is the amount of solute measured in moles divided by the volume of the entire solution in liters. Molarity is slightly temperature dependent because the volume of liquids changes a little bit with the temperature. So if you heat a liquid, its volume increases a little bit. If the volume increases, the molarity decreases. So molarity is temperature dependent. This is an illustration of how to make a solution. You measure out the amount of solute needed. Here, the illustration is making a 1 molar sodium chloride solution, so that would be 1 mole of sodium chloride in 1 liter total volume. So, of course, the balance doesn't weigh in moles, so you have to calculate the mass. You weigh that out, you add some water, you get the sodium chloride to dissolve. We did this back in experiment 4B. You get the sodium chloride to dissolve, and then you fill it up. There's a mark on this neck to indicate the stated volume. This is a 1 liter flask, and so that would be 1 liter. Then you would cap it, and you have to mix it very thoroughly, because with this narrow neck, you can't just give it a few shakes and have it be mixed. Any questions? Molality. This is not a typo. It's not a misspelling. I've had students get a question wrong on the exam because they thought I just spelled molarity wrong. And so they did the wrong calculation. I don't make typos like that. I do make mistakes sometimes, but not like that. Molality, just got an L here. This is the amount of solute, again measured in moles, but now we're looking at the mass of the solvent in kilograms. So if we had 1 liter of water, how many milliliters is that? That would be 1,000 milliliters, right? And if the density of water is 1 gram per milliliter, that would weigh 1,000 grams. How many kilograms is that? 1 kilogram. So molality is going to be similar in value to molarity, but there's a very important distinction. We're not looking at the volume of the solution, we're looking at the mass of the solvent. The reason that molality is useful is that it is independent of temperature, because the number of moles doesn't change with temperature and the mass of the solvent doesn't change with temperature. So molality is independent of temperature. This is abbreviated with a lowercase italicized m. Like, that's not confusing, right? So we have the lowercase italicized m. That's moles per kilogram. And we have just regular m. That's meter. Then we have capital M. That's moles per liter. Yeah. Not the greatest. Okay, parts by mass, parts by volume. So these are related to percent. Here we are looking at the ratio, the mass of the solute to the mass of the solution. So I've described percent before as the part divided by the whole times 100. That equals the percentage. Here in the solution, the part we're interested in is the mass of the solute, and the whole thing is the mass of the solution. The mass of the solution is the solute plus the solvent. I will try to trick you on the next exam with a question like this by giving you the mass of the solute and the mass of the solvent and asking you to find one of these kinds of units. And you have to add them together to get the mass of the solution. So this is the general idea, the part over the whole, and then it's multiplied by a factor. And the factor you choose is whatever is needed to make it a reasonable number. So if it's percent, cent refers to 100, so we multiply by 100. Percent is literally parts per 100. So if we have 14% by mass, that's 14 parts per 100 parts, 14 grams of solute per 100 grams of solution. And we've used that as a conversion factor earlier in the semester. Parts per million and parts per billion are used for very low concentrations. Again, it's mass of solute divided by mass of solution, but now instead of multiplying by 100, we multiply by 1,000,000 or 1,000,000,000. So if we see something that's 15 ppb, that stands for parts per billion, then that would have 15 grams of the solute in 1 billion grams of the solution. So you can take parts per million and parts per billion and make those into conversion factors also. We did that with mass. We can also do it with volume. Now we're looking at the volume of the solute divided by the volume of the solution. It's still the part over the whole, but we're looking at volume instead of mass. So 22% ethanol by volume would be 22 milliliters of ethanol in 100 milliliters of solution. It's also possible to do a mass to volume percent. So that would be grams of solute per grams of solution. I'm sorry, not grams. Per milliliter of solution times 100. It's the part over the whole, but now it's a mass and a volume instead. We don't do that much in chemistry, but it's used a lot in medicine. Okay, so let's do some practice problems. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. These problems are dimensional analysis problems, and they also involve some critical thinking, some problem solving. So if you're not sure what to do, a good place to start is by writing the numbers down with their units and just sort of seeing what you've got. So the first number is 355 milliliters. Do you think we need the 12 ounces in parentheses? No, that's an English unit. That's just there for reference to point out this is a can, a regular can of soda, 355 milliliters. And then we've got 11.5% sucrose by mass. Well, what does that mean? 11.5 grams of sucrose percent per 100 grams of solution. That looks like a conversion factor. And then they gave us the density, and whenever they give you the density, you think, I'm probably going to have to use that. Grams per milliliter. So what am I trying to find? Grams of sucrose. So I'm going to write out a path here. So I'm trying to find grams of sucrose. I've got this stuff. This grams in milliliters, is that grams of sucrose per milliliter of sucrose, or what is that? Is that the density of sucrose? Density of the solution, right? That's the density of the solution. So that means that's grams of solution per milliliter of solution. So I want grams of sucrose. I have this milliliters, I have grams sucrose per gram solution, I've got grams solution per milliliter solution. Both of these look like conversion factors. I can't use 355 milliliters as a conversion factor, so I probably want to start with that one. So if I start with 355 milliliters of sucrose or solution? That's the solution, right? What could I change that into? I could change it into grams of solution using the density, right? Or I've got milliliters of solution, I could go to grams of solution. And what can I do with this? I can get to grams of sucrose. So it ends up being 2 steps. Any questions? If you haven't learned how to put a problem together like this, it's not too late. I'd be happy to help you. So now that I have my path, I'm just going to follow the path. I've got 355 milliliters of solution. And I'm going to change that into grams of solution, dividing by milliliters. So the units cancel out. It's 1.04 grams of solution per milliliter. And then I'm going to put grams of sucrose on top and grams of solution on the bottom. And that comes from the percentage here, 11.5 grams of sucrose per 100 grams of solution. Calculator's saying 42.458. We should think about significant figures, right? So we've got 3 here and 3 there, 3 there, so let's keep 3. And, oops, would round that and say 42.5 grams of sucrose. That's a lot of sugar. Any questions? Yes. Yes. Yeah, so they say assume a density of 1.04 grams per milliliter. This solution is sugar, which is a solid, dissolved in water. And so the density of water we should know is 1 gram per milliliter. The density of the solid sugar is not going to do us any good. So we should be able to assume that this is the density of the soft drink, of the solution. Yeah.
Is that the soft drink they use water, so kind of convert the 3.55 milliliter to like 3.55 gram?
No, the 355 milliliters is the volume of the solution. So the amount of water in there is less than 355 grams. because the rest of it is the sucrose. Mole fraction. We used mole fraction when we did mixtures of gases. It's the same idea here. So mole fraction is given the symbol capital chi. So the moles fraction is the moles of solute divided by the total number of moles. It's a part over a whole, but not multiplied by anything. And it's the moles, not the masses. So we get amount of solute in moles divided by the total amount of solute and solvent in moles. So it's going to require some adding. We can take that mole fraction and multiply by 100, and that'll give us mole percent. Okay. So here we're going to practice doing some of these concentration calculations. A solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. I'm just going to start at the top. So, molarity. What are the units of molarity? Moles over liters. Right? Moles of solute per liter of solution. Well, did they give us any of that? They gave us the volume of solution in milliliters, right? So we could convert that to liters, 0.355 liters. I need to know the moles of sucrose. They gave me a mass. Well, I can take care of that. 50.4 grams of sucrose. They gave me the formula. And I want to convert that to moles. So I'm going to put moles on top and grams on the bottom. I need the molar mass to do that. So 12 times 12.01 plus 22 times 1.008 plus 11 times 16, 342.296. Nope, put it in the wrong place. 1 mole, 342.296 grams. So 50.4 divided by that, 0.1472. The starting mass had 3 significant figures. You really should keep 2 extras until you're done with the calculation. I see this causing some errors in your lab reports, because not only do you round it to the correct number of significant figures, some people are rounding it to fewer than that. You've got 4 sig figs and you round it to 2. And then you end up with all your molarities being exactly the same, and then you get a standard deviation of 0, and you're like, wow, I'm so awesome. No, you're not. So when in doubt, keep extra digits. You can always knock them off later. So I'm going to keep those 2 extra digits there. That's my moles, 0.14724 moles. And I divide that by the volume in liters, and I get the molarity, 0.41476. I'm going to round that 0.415, and I can write that as moles over liters. That's the same as 0.415 capital M. The capital M is shorter, it's on one line, and so, it's just a shorthand. We use it so much, but it's very important to understand it's moles per liter, not moles. Okay. The mole fraction. This is the part over the whole in moles. So this is going to be equal to moles of sucrose divided by moles of solution. So that's going to be moles of sucrose, I'm going to call it suc, plus the moles of water. Well, I know one of these. I just calculated the moles of sucrose, so I can put that in there. How many moles of water? They didn't give us that, because that would be too nice. The blue stripe is very decorative, but I need space. So they gave me 0.332 kilograms of water. Well, we could convert that by writing what kilo means instead of the kilo. Kilo means times 10 to the third, and then grams of water. And that's not proper scientific notation, but your calculator doesn't care. So there's grams of water, and then it's the same idea as we did with the sucrose. I need to convert this to moles. I need the molar mass of water, which is 18.02. So 0.332 times 10 to the third divided by 18.02. So this is 18.423 moles of water. I did that wrong yesterday, but I'm pretty sure I did it right today. So that goes down here. We have to add the moles of each so we can get the moles total. And the unit down there is mole. What happens to the units here? They cancel out. Moles cancel moles. The mole fraction is unitless. When you do this math on your calculator, be careful. So I'm going to do 0.14724 divided by, and then I'm going to use parentheses 0.14724 plus 18.423, close the parentheses, press equals 0.00792. In terms of significant figures, you should really add those together to see what you get. I've done this a few times, so I can tell you you'll end up with 3 significant figures down there as well. So my answer is going to have 3. So the mole fraction would be rounded to 0.00793. Remember that these leading zeros are not significant figures. You don't count those. If you count those, then you end up with a lot of rounding errors. I'm going to put a box around this one too, because that's a final answer. Any questions? What are the units of molality? Moles of solute, so here sucrose, per kilogram of solvent, which is the water. Well, we have those values. We calculated the moles, 0.14724 moles, and we were given the mass of water in kilograms. This would also have 3 significant figures, 0.44349. You could write that as moles per kilogram, rounding that to 0.443. We can also use that potentially very confusing lowercase italicized m. 0.443 moles per kilogram. Any questions? Letter D is mole percent. Yeah, it's the mole fraction times 100. Oh, look, we already have the mole fraction. So this is equal to the mole fraction times 100. So that would be chi times 100. So 0.0079288 times 100. 0.79288, which will round to 0.793%. Any questions? Percent by mass. What is that? Is the mass of the sucrose divided by the mass of the solution. So we want grams of sucrose divided by grams of sucrose plus grams of water. And it's percent, so we multiply by 100. Well, they gave us the mass of sucrose, 50.4 grams. And we're going to divide by 50.4 grams. I'm going to leave the gram there. And the mass of the water in grams would be 332 grams. And here the units cancel out again. So 50.4 divided by the quantity 50.4 plus 332 times 100, 13.179. .2%. The common mistake students make in calculating a percent by mass is they'll take the 50.4 and divide by the mass of the solvent and multiply by 100. And sometimes it's pretty close to the right answer, but it's not the right answer. I guarantee you I will try to trick you with that on the last exam. You've been warned. So then it's not really a trick, is it? So the final volume of the solution is 355 milliliters. And you're asking what happened to it?
We didn't use it, right?
Well, we used it in the molarity.
Oh, I see.
So the molarity needed the volume of the solution. And the volume of the solution is not something that you can just piece together. If I were to look at the volume of sucrose and the volume of water and add them together, it wouldn't necessarily equal the volume of the solution. Any other questions? I'm going to do one more here and then we'll take a break. So here we're taking one concentration unit and converting it into another concentration unit. What's the molarity of a 10.5% by mass glucose solution? The density of the solution is 1.03 grams per milliliter. Well, let's just take our numbers and write them down. 10.5% glucose. So that means 10.5 grams of glucose per 100 grams of solution. Because percent is this many parts per 100 parts. And as long as you use the same unit on the top and the bottom, you're fine. And then we've got a density, 1.03 grams per milliliter. That's the density of the solution, so that's grams of solution per milliliter of solution. And what do we want to find? Molarity. Molarity would be moles of glucose per liter of solution. This one tends to give students more problems. This is a concentration. I could change grams of glucose into moles of glucose and 100 grams of solution into a liters of solution intact as a fraction and do that. Students tend to find that confusing. Yesterday I solved this problem by saying, well, what if we had 1 liter of solution? How many moles of glucose would be in there? But today I'm going to do it a little different. I'm going to say, well, let's just take this concentration unit apart and convert these two things separately. I have 10.5 grams of glucose, and I want to convert that to moles of glucose. And I have 100 grams of solution, and I want to convert that to liters of solution. I'm going to do those conversions, and then I'll divide the one by the other. So 10.5 grams of glucose, I want to get to moles, grams of glucose in the bottom. I need the molar mass. 6 times 12.01 plus 12 times 1.008 plus 6 times 16, 180.156. So 10.5 divided by 180.156 is 0.0582. 0.58282. 3 sig figs again. Moles of glucose. Then I'm going to take this 100 grams of solution and convert it into liters of solution. So 100 grams of solution. Well, they gave me the density, right? So I could convert that to milliliters. So I put grams of solution down here and milliliters of solution up here. 1 milliliter weighs 1.03 grams. And I'm trying to get to liters, so then I'm going to put milliliters and liters in here, and milli means 10 to the minus 3. So I've got 100 divided by 1.03 times 1 EE minus 3, 0.097087 liters. Now, sig figs. What about this 100? How many significant figures does that 100 have? It's infinite. It's an exact number. The sig figs are in the 10.5. Percent is defined as per 100, per exactly 100. So this would have an infinite number of significant figures. This is also an exact conversion, but the 1.03 has 3 sig figs. So we got 3 sig figs there. So molarity is moles divided by liters. So it's my 0.058282 moles of glucose divided by the volume of solution in liters, 0.097087 liters. Zero point 60031. We could write that as moles per liter, or 0.600 capital M. Any questions? You should be able to do a problem like that on an exam.